for this example, again, let me try to make a complete one, and then we'll gradually simplify. Okay, so for this one is the real S, imaginary X, and again, for these systems, we have poles here and -1, okay, and we have 0 and -3. And for this path, we can select things from here, and we bypass, so not to include this one. Okay, for this one, let me try the complete one. So this is the direction of the path here. Okay. So for this case, the GH will get this prepared, that one equal to K omega squared plus 9 and omega squared plus 1. Okay, G J omega. So on the for S equal to J omega, that means on the imaginary axis. Okay, so let me deal with the point until here first. Okay, so here we have this one, and the angle I get prepared is 3 plus J omega minus J omega and minus 1 plus J omega. Okay, so
question.
Yes.
So that's shouldn't one of the poles be a positive one?
Oh yes. Sorry, my mistake. That should be here. Thank you. So for this one, again, right now for the first portions, I try to plot this point. The sampling point is taken from the imaginary axis. So in this way, we only substitute the S equal to J omega into here, and here I just try to prepare. So the phase for this case, the first one is pretty straightforward, arctangent of omega over 3. And for the second one, that is contributed by the S here, and that is 90 degrees. Doesn't matter the. How about for this one? And again, for this one, we can plot it here. So the complex plane, the -1 is here, and omega. So say if omega is positive, and so the point is here. Okay. So basically, that phase angle is this one. That means this angle is how much? This is arctangent. Again, if you take this triangle here, this is 1, the height is omega, so this small angle is arctangent of 1 omega, and this is 90 degrees, excuse me. So this one is 90 degrees plus arctangent omega, so this is when omega is positive, okay? Or on the other side, when omega is negative, then basically, for example, omega negative, that means here, so the angle is how much? Is this? This is minus 90 and minus a little bit more. And this one basically is 1 over the square root of omega, right? Again, this one, if you take this small angle, that is arctangent, right? Be good? Okay. So under these situations, and we can start it. And how to start it? Let me take the sampling point. So this is S1. So when S1 equal to J infinity, so GH. Okay, so GH, because the omega here, and that's going to approximate equal to 0. And then for GH, this is on the positive, we go to this formula. So this is 90 degrees minus 90, and 0 minus 90. So basically this one, GH, equal to minus 90 degrees almost. You good? Okay, and now I've taken this one. So basically this is the intersections of the straight line with this small semicircle. Okay, this semicircle again is our way to bypass the one we don't want to include this pole in this loop. So we bypass it. So here this is one, S2. So S2 equal to J equals 0. Okay. So under this case, then you can see due to this omega here, that is go to infinity. You good? Give me a smile. Less than 10 days, you can walk to the ceremony, right? And then for this one, again, when we plug in, so this is 0 degrees, and let me do this calculation, 0 degrees minus 90, minus 90 plus, and this one is how much? That one, almost 90 degrees, right? So that is almost, wait a minute. No, sorry, I always make a mistake. This is 0 degrees. Arctangent 1/0 is how much? Arctangent of infinity, so that is 90 degrees.
So in your diagram of error, is that assuming that the pole is at -1?
Say that again?
In the diagram to your left, there's the
Okay.
peripheral thing. Is that assuming that there's a pole at -1?
No, for this one, for this diagram, I simply want to say is, for this one, minus 1 plus j omega. Yeah, I would simply want to, in this diagram, I simply want to determine the phase angle for this complex number.
And that corresponds to?
That corresponding to when omega is positive, corresponding is this one, right?
Right, what part of the characteristic equation?
It's the S-minus.
That's not right.
What portion of
Or I'm just confused because on the diagram you made, it's at -1, not positive, or to your left. It's around -1. Maybe I'm just not understanding what the diagram's about.
Oh, here for this one I just make a scale. Maybe in this way I erase it. I just want to make scale. Basically here in this diagram, this simply is one I want to determine what is the phase of this number. That's it.
Good.
Good. Okay. So for this case, when omega becomes zeros, then basically that. Okay. So for this case, you can see when omega becomes 0, then that point is pretty much here. So that should be 180 degrees. Then let me see where the mistake I made. 0 degrees minus 90. And this one is 180. Okay, that should be good. So in this way, this case will be equal to how much? Minus 90 minus 270. That should be good. Be good? Okay. Any questions? Okay, so now for this one, and then the next one I want to make is this, and I want to describe is what is the sampling point about this circle that bypassing the origins, where there's a one pole here we don't want to include. So let me use the green line. The green circle, basically this one is a circle with radius epsilon, and epsilon is very small. Okay, and all the points on the semicircle. And if you remember, in earlier when we talked about the complex numbers representation, for example, if this is the A plus JB, this is a real as imaginary x, okay? So that is the one representation of a complex number. Also, that complex number can be represented by, say, if this is the magnitude, let me call the magnitude, whatever the number, give me the number, say m, okay? And if this is the phase angle phi. So we also have a second representation is in terms of the magnitude and phase angle, right? Okay, good. So right now I'm going to adopt this one because that one will be easier to describe the point on the circle. So this one, the point will be anything, all the points on the green dot will be equal to epsilon with the angle phi. What is the angle phi? Angle phi is starting from here. The point at here is how much the angle is 90 degrees, right? And then to follow up our circulation in this way, so everyone head up and look at here. So for this one, we sampling is starting from here and under this circulation to here. So that means under this circulation to minus degrees. So in this way, follow up our past directions, the phi equal to is from 90 degrees to, let me write here. The phi, the angle is 90 degrees to minus 90 degrees. That is a range, that is a domain we consider here. Be good? Okay, so now here, so for S will be equal to epsilon. JP here, okay? So phi equal to 90 degrees, change to minus 90. Okay, so we keep this in mind. So now we calculate the magnitude. So for the magnitudes right now, again, here we have to look at here. Because right now on the green dot, that is not only the point on the green portion is not pure imaginary numbers anymore. So we shouldn't apply to this. We should back to here. So basically here we apply for is as equal to epsilon JV. We have to apply to the original, right? Because this number here on the green dot actually representing is they should have a real part there. Be good? Okay, so now for here we basically plug in and the magnitude we can do the calculation. Again, due to the as here. Let's do this one. Okay, so for example, the GH, and again using the green colors and corresponding to that is the calculation of these big portions. So GH will be equal to K and S plus 3 and S minus 1. Okay, so if you are really picky, want to do the calculation, look at here. For anything we've been through is this one. So for this, if you want to further simplify this version, basically that is m cosine phi plus j sine phi. And so that is m cosine, the real part is this, and imaginary part is this. If you really want to do it, and you should do it in this way. So let me do just one time. So basically this is K. For this one, what is S? S is a real part here, so that is the epsilon cosine phi plus j sine phi and plus 3. So let me get the 3 plus to the front here. 3 plus this one. Okay, so let me leave the numerator below. So for this one, that should be equal to K, and then on the numerator, that should be the real part square, 3 plus epsilon cosine phi square plus epsilon sine phi square, right? So you can repeat for the denominator terms. Be good? Be good? Okay, if you really want, if I'm really picky asking you to show me the detailed calculation, do this. Okay, under these situations, because our epsilon is equal to 0, almost equal to 0, so let me use the counter here. So because epsilon equal to 0, so basically this term almost approximates the real part equal to 3. This one almost gone. So that means for these calculations, this one approximates equal to k, this one equal to 3, and this one equal to almost is minus 1, right? How about this one? That one has nothing, your epsilon there. So that contribution is due to this existence that is approaching to infinity. Good? So the same thing, the same calculation for all the points on the green dot circle here. So for this portion here, the magnitude for sure that should be infinity. Should good? Okay, now we can try phase. Okay, the phase, again, that is phase due to k, which is 0, plus the phase due to s plus 3, minus the phase of the denominators, the phase s minus 1. Okay. Now, again, we know the s is a very small complex numbers. So basically here we can approximate this one is 0 degrees, right? S is a very, very small complex number plus a big real number basically here. That's basically the point should be here, about 3, around 0.3. So this number is 0 degrees. Good? How about for this? The same thing, this one, the S is a very small complex number, so say around in here, something just nearby. And plus the minus 1, so basically that one, that point is pretty much here. This is S equal to minus 1, so that point is about here. So that angle is how much? 180, right? Okay, so this one is 180 degrees. If you like, you can check the minus 180, but either way, okay? How about for this? This one simply is dominated by our angle here. So basically this phase angle is simply phi, right? Okay. So phi is changing from 90 to minus 90. So this result will be equal to plus 180, so that is 270, and changing to 90 degrees, right? Is that right?
They're both negative.
Negative here?
That's the opposite street.
Yeah. Minus. Okay, so basically here from this way we conclude is changing from minus 27 degrees and to minus 90 degrees. You good? Okay, so once we've done this one, then again we can apply the symmetries and we can ignore the lower portion. Basically that will be repeated with simply reflected. So we can give a try. This is the real part of the GH. And let me put this in imaginary GH. Okay, so where is S1? S1 is almost 0 and minus. So let me say S1 is here, this point, and this is the minus 90 degrees. So right now I'm labeling its corresponding S1. So then let me label that corresponding capital S1. Okay. And then S2, and that is from this point, and then we go further, and the end up is the 270 and minus 270, basically minus 90, minus 180, minus 170. So that should be in that portion. So that means here I would say, so starting from here, and then like going, if we have a few more points in between, we can do it, but basically that is here. From minus 90 and 180 until minus 270, and then here this point basically is at here, so that is at infinity. So that point is basically is way above the imaginary axis. Very good. So this is our S2. Okay. I think you follow me very closely. Let me make a bigger plot. Okay, let me continue. It won't hurt. So right now we are to here, so we done this one. And now I want to proceed to this one. So that is at infinity. So it's changing from minus 270 to minus 90. So basically changing from here. And so basically minus 270 and gradually say 270, say 260, and 280, etc., etc. So basically that counting is in this way to back to here. Be good? So here is the directions. Okay, so I make a wrong scale, so that's the reason I prepare for the second one. You can keep it. You can keep this one, but to make a better scale, I think will be better here. So S1 is here, and then we make it from minus 90 and go to this is S2. Okay, that is at J omega. So S1 is very close to 0 here. Okay, and then from here we have go to. So this is the underground one. Let me label it. So those one are corresponding, is a point corresponding to the green dot our the Nyquist plot here. Okay. So it come to minus 90. So let me continue. It's come to minus 90 here. So those dots. So basically this point corresponding is infinity at minus 90 degrees. Okay, so the final point is about there. So that one ending, that point marks the ending of our last point, which means mark the plotting of this point. Be good? So again, let me say this is the, say S, let me say S, whatever, S star, let me say S star. The S star is this point, and that point corresponding to our plot is this one. That point just below the origin, that is S star here. Okay? We good? And in our calculation, that one corresponding is our last one. The last point would be 3. Okay, so this portion basically is about in the upper portion, then we make symmetric. So symmetric, probably let me use dash to draw this one. So that is a dash. Okay, so that makes the whole complete plot for this. You good? And again, you might wondering what is the point on this big circle. Again, those points on the big circle here, I pointed using dot. Basically, those points will be surrounding here. You keep plotting, you keep plotting your point, your Nyquist plot here around the origin. That's okay. Because the same reason as the previous example. Okay, again, those sampling points onto the biggest circle with the radius infinity, that one corresponding to basically is a point keep darting around here. If you like to zoom in, you can zoom in, but here for details we can ignore. So basically you know that's kind of segregations of many points around the region there corresponding is this one. Good? Any questions? Yes.
I had a question about the final. I know you were talking about possibly switching it. Did you make it?
The final, I'm kind of thinking, I will keep trying. Let me finish this first.
Oh, okay.
So if no further questions, then we can apply the stability. Yes.
Can you repeat the last portion?
Last portion?
Yeah.
The dash one?
Yeah.
Okay. The dash one, basically, the dash one is to corresponding to the plot from here, the point on this point, on those circles, on those. Okay. So this one, again, we apply the symmetry. The corresponding Nyquist plots of those points, they will be symmetric corresponding to this. So, again, this is the plot for the points on the those are the plot of the point corresponding to this portion. And we make symmetric, and that will correspond to this one. So here you can plot the dash like this. Yes?
What's the direction of the dash?
Yes, let's do it. That's a good question. So from S1 to S2, so here is a 1, so here. Then with complete, that should be go to here. Like this. Good? Okay. Right now for this one, when we plot this, the influence of K has not been showing in here. This example is a little bit different from what we've been exercising. This involves K. So here my question to you is this. How do we find the intersection here? The intersections of the Nyquist plot to the real axis. The reason why I'm asking is this. Again, here we're going to apply the Nyquist stability, the theorem, n equal to z minus p. Let's look at these systems. And for stability, for a stable system, for stability we're asking, z must be equal to 0. That means no real, no root of the closed loop characteristic equation is on the right hand side. So we're asking for this. So we use this way. That means we have to is n equal to minus p. And for this example, what is the number of p? 1. Right? The number of p is the number of the poles being enclosed in this Nyquist plot, p equal to 1. So, and for this example, p equal to 1. So that means this is minus 1. Okay? So that means n must be equal to minus 1 for a stable closed loop system. What that means, the n equal to -1, in terms of our plot here, we must determine for a stable system, we have to say, if I ask you to design the value of the k for the system to be stable, for example, if the system will be like this, GH. If this is our closed loop system, which containing one unknown parameter k, if I will ask you to determine the range of the k such that this system is stable based upon these informations, how can you answer these questions? Again, the rule is this. By all means, you have to make sure this is satisfied, right? What means this satisfied? That means the -1, 0 is enclosed or encircled in the loop. -1, that means in the the clockwise directions. Right, so that is the interpretation of this means. We'll look at this one. So right now this is in counterclockwise directions, right? So if we follow this one, if you can see any point in this segment is enclosed by counterclockwise. Counterclockwise. Any point in this range is encircled clockwise. So let me know, to make this satisfied, this point must be in which range? This one. Right? You good? So in this way, you have to design your case such that to make the -1, 0 is in this range. You good? So that reason why I'm asking to you, what is the intersection? Intersection, this location is very critical. That will determine the boundary of this range. Let's do it. Okay. So for this one, the Nyquist plot of GH intersect with the real axis at where? And I'm going to determine this one. Intersection, basically this is a complex number. So basically GH, if you plug in, you can see these intersections happened in this segment or in that segment. Basically corresponding is these numbers. Again, intersection is this point is belonging to this segment or this segment, and that corresponding is our imaginary point. So always, you want to find it, you always plug in s equal to j omega. Assuming this is alpha plus j beta, if you simplify these things, okay? How to do it, just do it, okay? And then intersection, that means you set beta equal to 0. This alpha is a function of k, beta is a function of k, and omega whatever. Okay, so let me do it. Let me do it here quickly. So GH will be equal to K and J omega plus 3 and J omega and J omega minus 1. Let me do this one. So basically here this is K times J omega. I'm going to simplify this one. So this is 1 minus omega J omega minus 1 and J omega plus 1. So J omega plus 3 and J omega plus 1. Okay, so that is K J omega and minus omega square plus 1 minus 1. And this one will be equal to minus omega square plus 3 plus J for omega. Be good? Okay, so now for this case, this has the imaginary portions. So we imaginary portion for this one is equal to Kj omega, and then for this one I take the real part, minus omega minus 1 minus omega plus 3. Be good? The first of all, you apply the complex algebra to simplify this, and your job is to find what is the alpha is a function of K and omega plus J beta, that is a function K omega. That is the imaginary part, that is the real part here. And imaginary part right now after simplifications, this is the imaginary numbers. So to take the imaginary part, I simply take this portion, is this one. Be good. I set in this equal to 0 because I want to find the intersections. Intersections with the real axis, because on the real axis, the imaginary part equal to 0. So from here, omega equal to square 3. Okay, so the real part equal to K J omega times minus omega minus 1 and J for omega, and you plug in omega equal to 3 square 3. And that one will be equal to K, exactly, hopefully. Okay. Minus K here, sorry. So therefore it intersects at minus K, 0. At the intersections is the imaginary part equal to 0, real part equal to minus K. So therefore intersecting at minus K, 0. Be good? You have to get it to do the homework. Ask any questions now. Good. Okay. So that means intersection linear label it. So this point is minus K, 0. Okay. So now we come to our point. For stability, minus 1, 0 must be here. So that means minus 1 must be within this small circle, right? So that means K, can you tell me what is the design range? Minus K must be to the left of minus 1. K must be greater than 1.
What happens at K equals 1?
Or equal to 1. When K equal to 1, that's called the marginal stability. Okay. Good.